family. From the town of Bedrock, they're a page right out of his story. Let's ride with the family down the street, through the courtesy of Fred and Pete. When you're with the Flintstones, have a yabba-dabba-doo time, a dabba-doo time, we'll have a gay old time.
Hey again. The sampling distribution concept that I talked about in the other video is an important one, and I find that it's sometimes confusing, so I'm going to offer up this additional explanation. So let me, if it was unclear, let's go through this and see if this makes a little bit more sense. Let me present it in this way. As I mentioned, that then we're turning a corner and going from individuals and their scores to focusing on groups or samples and their means, and there's the scores that make up their means. And we're turning a corner in going from descriptive statistics onto the inferential statistics, which help us understand and make decisions about a population from a smaller subset like a sample. So as you're going to see, we are going to get to use everything that we've learned, though, especially about normal curves. So this is a great thing. All right. Now, to understand the concept of sampling distributions, let's go through another example. This one's going to be kind of so simple it's silly. But suppose a professor gives an 8-point quiz to a small class of just 4 students. And we see the results of that quiz on the screen here. So a student got a 2, one got a 6, one got a 4, and one got an 8 in just kind of unsorted, random, maybe the order that they were scored. Okay, now assume that there's just 4 students in this entire population. The class is this is my population of 4. Okay, so we're going to deal with the really ridiculously small here in this example. So a gigantic population of just 4. And so we can calculate the mean of that population, so we'll call that mu. The population mean is, of course, going to be equal to the 4 scores added together and divided by 4. So you add those up and divide by 4, and that equals 5. So the mean score is a 5 on this quiz. I don't show the work here, but likewise we can calculate the standard deviation for the population. And I've done that for you, and it is equal to a sigma. Sigma is equal to 2.24. So the mean is 5, and on average, students differed from 5 by about 2.24. Or in other words, the students differed from each other by approximately a mean of approximately 2.24. All right? Now, if we graph this population, if we make a frequency distribution of the raw scores for this population, it looks like this thrilling graph here, all right? And this is not a very good graph. We jump from 2 to 4 to 6 to 8, and I don't have enough room for 3, 5, and 7 in between there, so it's kind of not the best looking graph, but that's beside the point. The point that I'm trying to make here is that this frequency distribution is anything but normal, all right? It's flat, it's rectangular, it's sawtoothed, if you will, if you want to give it a shape. It's not normally distributed, and indeed nothing for 4 people could be normally distributed, or 40, or 400 for that matter. A normal distribution for you to get that nice flowing true normal shape requires great big populations, enormous piles of data. So, but still, no matter how much you squint your eyes, this does not look like a normal distribution. That's an important concept I want to make here, all right? So we're starting now not with some population variable that's normally distributed like we did with intelligence and all the things that we did with z-scores. To use the z-scores for individuals required that this population data, that the variable be normally distributed, okay? Not the case here, okay? So there's my population. There's my frequency distribution of raw scores. Now let's take this silly scenario and let's make it even sillier. Imagine that we want to sample this population. We want to study this population, but gee whiz, populations are always too big to study, right? We can't possibly study all 4 people in this population. got no time or money to do that. We're limited to just studying samples, okay? And specifically, we're going to use a sample of 2, okay? 2 students at a time. Now, we're going to do something else that's weird, especially in the context of doing research. You would never do this in research context, even with a big population. But pretend that we're going to sample from this group using a process of sampling with replacement. I've mentioned this before elsewhere. When you sample, you can either sample with replacement or without replacement. Kind of, we talked about this when we were talking about dealing cards out of a deck. Okay, if I draw a card and look at it and then put it back in the deck, that's called sampling with replacement. Shuffle up the deck and then draw another card. All right, but if I take a card, if I take card or cards out and put them on the table, and then maybe calculate the probability of the next draw of the card. Okay, there's now fewer cards in the deck. One or more of them is now on the table. That's called sampling without replacement. Okay, when we do research, we're essentially always sampling without replacement. We draw people. When we do studies, we get volunteers. We get data from them once. Okay, we don't replace them and then potentially draw them again. We don't want, we specifically tell people when we do research, not to sign up for the study a second time. We want just one, we want their data just once. Okay, so in real life, sampling without replacement is the norm when we do research. Okay, so for no good reason, I am going to, for this example, I'm using sampling with replacement. Okay, so back to the business here. We got a population of 4 that we have. It's too big to study. I'm going to study samples of 2 at a time from this population, but actually sampling with replacement. So I'm going to take data from one person, take one quiz score and look at it, throw it back in the population, and draw a second one. Okay. Now, of course, that means I might draw that first person twice. Okay, so that's why it's kind of silly, but here we go. All right, so again, here's the scenario. I'm going to randomly select a score, look at it, record it, throw it back into the pool, and select a second score. And then I'm going to calculate the mean for each of those pairs. So I'm going to do this over and over again. I'm going to draw, one, record it. The second one, record it. Pause, calculate the mean of those 2 numbers, and then do it again. All right, we'll do that I'll do that until I get every possible every possible combination, not necessarily unique, every combination that I can do. Okay, now if I do that, I'm jotting them down and, ignoring any repeats. I'm just, doing that for every possible combination. And I'm going to make a table showing all the possible scores of their means, and here it comes. Here they are. So I can get one way to, I could, the first, in this sample, I drew the 2, threw it back, and I happened to draw it a second time. Calculate the mean of 2 and 2, and that is, of course, 2. Okay, here I drew the 2 and the 4, and the mean of 2 and 4 is, of course, 3. I could do the 2 and the 6, and the mean is 4, and so on. Okay, so for each of the possible combinations that I can get up to, the last, and putting them in an order here, the last possible combination I can get is draw the 8 twice, giving me a mean of 8. Okay, so from a population of 4, doing it with this weird method of sampling with replacement 2 at a time, I have a combination of 16 possible samples, unique samples I could get. Okay, all right. Now, in the one hand, they're not. I hesitate to call them unique because, look, for example, I can draw the 2 and the 4, but I could also draw the 4 and the 2. Both give me a mean of 3. So in a way, they're not really unique, but there's unique orders in which I do it. Okay, so anyway, I have 16 possible unique samples and therefore means that I can get using this technique. So that's all of them. This is all possible samples. If I do any other samples, they're going to be repeats. Okay, if I do the 8 and the 2 again, I already got the 8 and the 2. I already got the 2 and the 8. Okay, I got every possible combination here, all 16. Okay, now these are no longer individual scores now, right? These now represent means for the 16 samples. So I'm not talking about 4 people anymore. I'm talking about 16 possible samples and 16 means representing those samples. So here's a table. Let's make let's make a graph of that. You know, tables and numbers are hard to read, so let's make a graph showing this. Now, when we make this graph, it's going to be another kind of frequency distribution, but I want to give it a unique name. So I want to plot how often, how frequent each of these means is, instead of plotting how frequent each of the 4 scores occurred. Okay, so this new kind of distribution is what we're talking about here, sampling distribution. So here's how we create a sampling distribution. Again, sampling distribution is short for a sampling distribution of means. So I want to show a sampling distribution of all possible means from that population of 4 being drawn 2 at a time with replacement. And here it comes. Okay, as I pointed out on the table before, there was one and only one way to get a mean of 2. I could draw the 2 and then the 2 again, and there was only one way. So there's one block in here representing the mean of 2. Likewise, on the other end, there was only one way to get a mean of 8, and that was to get the 8 and the 8 a second time. And you could that was the only way you could get that, get the 8 and then the 8 again. But for a mean of 3, there were a couple of ways I could get a mean of 3. Okay, I could get the 2 and the 4, or I could get the 4 and then the 2. Both of those gave me means of 3. So there's 2 and only 2 ways, 2 unique ways to get a mean of 3, and so on. Okay, now, again, a raw score frequency distribution is showing just that, how frequent raw scores occur. We saw that earlier, the rectangular distribution. It was not normal. Look at this one, however, now. It's not really a coincidence. It's not really a unique thing that all of these possible samples have piled up in this kind of interesting shape. All right, now that's only 16 numbers, 16 means here. And as I said a moment ago, 16 and even 60 or 600 would be too few to give me a normal distribution. But if you squint and use your imagination, when you look at this, you can kind of begin to see that it sort of resembles a normal distribution. Okay, most of the samples were in the middle around the raw population mean of 5. Okay, the further away you got from a mean of 5, the less likely it is. Okay, just like in the concept of a normal distribution. The further away you get from the mean, the less likely it becomes. The closer to the mean you are in your score, the more frequent that happens. All right, so here's a sampling distribution of those sample means. A few more concepts to cover here. Okay, I'll skip this. Now, as we saw at the beginning, the mean of those 4 scores was 5. I added up the 4 scores together, divided by 4. It was a population mean, a mu of 5. Now I have 16 means assembled in this sampling distribution. I can calculate the mean of those 16 numbers. Add up those 16 means and divide by 16. And guess what? They too equal 5. Now, when we do that, if we calculate the mean of all of those means, that's kind of now a unique new thing. And we have a symbol for that, the mean of all of those means. We use the population value mu, the mu of the x bars, okay? X bars, again, is a symbol representing sample means. So all of these 16 are sample means. Those are all x bars, right? And the mean of all of those x bars is equal to this new formula that we use for it, this new symbol that we use for it, mu x bar, okay? The mean of means. And again, the mean of means is equal to 5. And that's not a unique thing. That's not a unique thing for this example. The population, the mean of means is always going to be exactly equal to the raw score mean for the population. Okay, that's an interesting thing, okay, as you'll see as we proceed. Okay, now, just like for the raw scores, when we could calculate a mean, we'd also like to calculate the standard deviation. We learned those two go together for ratio, interval, scales, variables like we have here. Quiz scores, these were ratio scales. And the two descriptive statistics that we like to use are typically the mean and the standard deviation. Now we have 16 numbers, 16 means. We got the mean of them. We can also get the standard deviation of them. Okay, now here's a portion of the way I calculated that. You know how to calculate a standard deviation by now. And to be consistent here, I'm going to use the similar symbol, okay? I'm going to calculate the standard deviation of all of those x bars. You'll see on the next screen that we unfortunately don't get to call it that, but if I was naming this, I would call this the standard deviation of the means. Just like a moment ago we had the mean of the means. Now we're going to calculate the standard deviation of those means. Okay, and I hope you remember how you do that. Oops, sorry. I get the, you calculate the deviation for each one of them. So you take the mean of 2 and subtract the mean of means of 5, square it. Take the value of 3 and subtract the mean, square it, and do that, and so forth and so on for all 16 numbers up to the last population, the last sample mean, sorry, was 8 minus the mean of 5 squared. Okay, so you do that for all 16, add them up, and divide by 16, and take the square root of that, and that bugger equals 1.58. Okay, so we have a standard deviation of the means of 1.58. Now, unfortunately, I don't get to name things. All right, I think that's a better name, but I didn't get to name it. Others beat me to it, and those people decided to call this the standard error of the mean instead of the standard deviation of the means. Okay, so this standard error of the mean, and often written SEM, often abbreviated further, just called the standard error. We often just call it the standard error, the SE. Okay, standard error. Now, in real life, that was simple. What we just did was simple because it was as simple a population as I could just about get, 4 people. And then doing it with that method of sampling, we had just 16 possible means, all right? Now, in real life, I want you to expand now. Now, think about real life. Let's say that a typical class, a typical classroom of students, 20 people taking a stats class, all right? That's just one fairly random constellation of 20 HPU students, all right? From a population of HPU students. Now, try to imagine all of the different classes that you could get, okay? There's 20 of you sitting in a room. Substitute one out. Take one out and replace it with another student. Boom, you got a unique class. You have a unique mean that you could calculate from those 20 people, okay? Take someone else out and put somebody else in, or take all 20 out and replace it with 20 different people, or 10 and 10, or all of the possible all of the unique combinations of 20 people. All right, bajillions of them. I don't even know how many. If we have 7,000, I'm not smart enough to do this. There's probably a fairly simple formula to calculate this. I'm not interested. But if there's 7,000 students, how many unique combinations of 20 at a time can we get? Tons. Good enough for me. It would be tons of means. I would, if I wanted to for some reason, I would never be able to take the time to do that, to get all of the unique combinations of 20, calculate their mean, throw them back, get a new group of 20, calculate their mean, throw them back, get a new mean, calculate their mean. So you just wouldn't do it. And that's a small population, just HPU. Cripes, that's one school out of thousands, all right? So for big populations, these numbers that we're kicking around, the mean of means and the standard error, these are very theoretical things. No one will ever go out and do it. We'll never get them for real. But they exist, right? They're out there. We just don't have the capability of getting them. But they're there. Well, we still would like them. We'd still like to use them. It turns out that a sample mean is a pretty good measure of the population mean. So we don't worry a whole lot about sample means, all right? But what about the standard error? Can we ever hope to get the standard error? If we can't get all of the means, how could you calculate the standard deviation, right? You need a mean to calculate a standard deviation. Without the mean, how could you calculate it? Well, it turns out the math nerds gave us a way to do it. So let me look at this formula down below. All right. This is a estimate. We call this an estimate formula for the standard error. To estimate the standard error, if you do know the raw population mean, standard deviation, if you know sigma for the population, then you just divide it by the square root of whatever sample size you're using, okay? Again, back to the classroom example. Let's talk about intelligence, okay? I know, let's say I was studying IQ again, all right? Now I got population data available for IQ, right? The population mean is 100, the standard deviation is 15. So if I'm going to do research with 20 at a time, so let's make n equal to 20, a class of 20, okay? What would the standard error be for all of those bajillion groups of 20? I don't have to go get them. I can use this little simple formula. So this is beauteous. This is transcendental, this formula for me, okay? This is a way for me to get that without having to get it, all right? And look at how elegant this is. In physics, and you know, everybody knows Einstein. Everybody knows Einstein's brilliant, famous equation, E equals mc squared. Famous. People love that formula. Not many people understand it or understand the ramifications of it. You know, energy equals the speed of light squared, well, whatever it is, equals mc squared, mass times the speed of light squared, okay? Everybody knows it because it's so simple. Exactly how you go from there to atomic bombs and atomic energy is another, you know, big kick in the pants, but everybody loves that formula. People put it on t-shirts and wear it around. E equals mc squared, and posters, and hang up pictures of Einstein. Everybody loves this guy. And people talk about how transcendental and beautiful that formula is, and elegant in its simplicity. E equals mc squared. Ladies and gentlemen, in psychology and social science research, this, my friends, is our E equals mc squared. This formula is why you are here, why you can be a psychology student studying research, and why we can go on to do research. Because we need the standard error, as you're going to see. We need it. But we'd never be able to get it. It would be too impossible to ever calculate, okay? But this allows us to estimate it with a great deal of precision. And so we get it. We get it without having to get it. And that is brilliant. That allows us to do research, as we're going to go on and see. Without it, we'd have to come up with some other method. I don't even know what that method would be. So this is transcendental for us. This is our E equals mc squared. I'm always tempted to make a t-shirt out of this and wear it around and be proud of it. Standard error is equal to sigma divided by the square root of n, okay? A tiny, 4 symbols, one of them used twice. I mean, just a handful of symbols in this simple formula allows us to do what we need to do. Let's try it out. Let's see. Okay. A moment ago, I showed you an abbreviated version of, the conceptual way to calculate the actual standard deviation, the actual standard error of those 16 means. I left them out in the middle here, but I could put them in. It was a small group, 16 of them, and do the math, and I wound up with a value of 1.58. So that I am calculating the honest to God standard error for those 16 is, I rounded it to 2 decimal places, 1.58, very precise number. All right, let's try that estimate formula. Let's give that a whirl. Okay. Way back at the beginning of this, I calculated the standard deviation for those 4 numbers. If you look back, you see that it's equal to 2.24. All right, so I know that the population sigma is 2.24. All right, I know that. That's not a guess. Plug that in. For the sample size, I was sampling 2 at a time, so n equals 2. So 2.24 divided by the square root of 2 is this, and I rounded to 2 decimal places, and look, 1.58 equals 1.58. Brilliant! Brilliant! Proof is in the pudding. The standard error estimate formula is pretty close enough to a dead ringer. I mean, if you did the decimal places, if you go out to several decimal places, it might be flaky, but to 2 decimal places of precision, it's exactly the same. All right, it does a outstanding job of estimating what the standard error would be. Okay, this is just a silly simulated little example, but if it works on the small, it works on the large. Computer simulations bear this out, you know, where we have access to real deals and we can simulate it on computers, we can see that it works. All right, this estimate of the standard error works. Okay, what's so great about this? Well, we would now have the mean and the standard error, and we would be able to go on and do all of the things with a normal distribution that we could use before. Now, if you're really paying attention, though, you would have. Let me come back to that. Okay, so let me first say what's cool about these sampling distributions. All right, so they're cool for two reasons, as we're about to explore. This is a part one of part two. Okay, to do this inferential stuff, we need the concept of sampling distributions together with a slightly more complicated thing called the Central Limit Theorem. So sampling distributions plus Central Limit Theorem gives us normal curves. All right? No matter what we started with, we'll get a normal curve. We started this silly example with a flat rectangular population distribution from 4 people. That was not normally distributed. Take samples, get a theoretical sampling distribution, and we could see that, oh, they arrange themselves in what's starting to resemble a normal distribution. So, for reasons that we're about to see in part 2, the Central Limit Theorem, they are almost always normally distributed, no matter what the population really looked like. That's cool. But what's really cool about it, well, since they're normally distributed, since sampling distributions typically are normally distributed, given the restrictions and limitations we're going to see next, it's normal. Normal distributions. You know how to carve up a normal distribution very precisely using 2 simple tools, z-scores and z-score table. Plug stuff into a z-score formula, consult with a z-score table, and boom, I can tell you about percentiles. Okay? So you could do it for an individual. You could say, hey, what percentile is somebody with an IQ of 110? Wonderful, that was awesome. Now you can take a group of 20 people, call them a sample, get their IQ mean. What if you had a sample of 20 people with an IQ mean of 110? What percentile is that group of 20 relative to their sampling distribution? Use it, z-score table and z-score formula, and boom, you'll have that answer. That's brilliant. That is magic. And that allows us to make decisions about likelihood, about probability. Let's go back to this, for example. Now, let's say that, let's put this in an experimental context, okay? So these are no, we're not just talking about kids taking a random quiz here now, all right? Let's pretend that I had that one group of 2 kids just took the test with a placebo. The other group of 2 kids are in what I call my experimental group, and I gave them a miracle pill, all right? I gave them a Fred Flintstone Barney Rubble vitamin. That's my miracle. A lot of people don't know that, all right? A Fred Flintstone Barney, whatever, the Barney Rubble in the bottle of Fred Flintstone vitamins that you might have taken as a kid. They're miracle workers. They make you brilliant. They make you smart. Okay, take one. So I give one group a Barney Rubble vitamin, which contains this miracle stuff, and the other group in the control group gets, I don't care, they get the Fred Flintstone or the Betty vitamin or something, all right? They get one of the other ones that doesn't have the miracle stuff in it. It's a placebo, all right? And then they take the quiz. Now, let's say that one of these blocks here, okay, the control group gets the kind of expected mean, all right? They get the mean typical score on the quiz, all right? The 2 kids have a mean of 5 on their quiz. But what if the other group, the group that got the Barney Rubbles, what if they had a mean of 8? What do you know about 8? It's out here in this getting rare zone of this distribution here. It's very unlikely to get the 8. It can happen, there it is, okay? But in that context, if one group got the 5 as expected and the miracle group got the 8, it starts to make you think about the Barney Rubble vitamin, doesn't it? It starts to make you think, well, they could have gotten it based on chance. Could have happened by chance, but it might have happened because of the Barney Rubble vitamin. Chance, Barney Rubble. What is the chance? What's the likelihood of it happening? Well, it was low. It's rare. Do you see where I'm going with this? I hope you see where I'm going with this. When we get control groups that are out in either tail, depending on which direction the thing's supposed to take you. Maybe a Barney Rubble vitamin makes you dumber, okay? Maybe it makes you do worse on quizzes, all right? What if you got this result? You'd have to sit there and weigh on the two, it's unlikely, it's possible, but it's unlikely that they did so poorly. But maybe my treatment made them worse, or maybe it made them better, okay? So that's where we're going with this. That's why we love this stuff, and that's why we love this formula. It allows us to do that. It allows us to take a sample and compare it with this theoretical thing. This is a pile of means that we would never get in real life, okay? This was just for 16. That was easy to get. Real life, our sampling distribution is out there, but we'll never be able to see it. We're never going to go get it for real. But we know what it looks like. In the next episode, we're going to see the Central Limit Theorem. And the Central Limit Theorem, in a nutshell, tells us that, hey, given these right conditions that I'll explain there, we're going to get a normal distribution. All right, good. If you give me a normal distribution, give me a z-score table, and give me a z-score formula, I can tell you the percent likelihood that something happened. I can tell you the percent likelihood of getting that mean up here. And then I can make a very informed decision about that was very unlikely, that was very rare. On the other hand, I did something to those people. Okay? That doesn't prove that the treatment worked. It does not prove. Scientists don't prove. Okay? I can't prove that the treatment worked, but I can compare it to, very unlikely. Very unlikely that it could have happened by itself, but with the treatment, makes sense. There you go. That's the concept of inferential statistics. There's our concept of sampling distribution. So take a look at these two videos. Take a look at the relative content in your textbook. And the textbook's right there. Okay? Look it up, read it, look at these two videos. Let me know if you still have any confusion of what sampling distributions are. At this point, I want you to be able to tell me with perfect fluidity what a frequency distribution of individual scores is, what a sampling distribution of means is, how they're similar, but yet how they're different. What do they have in common? How do they differ? Okay, great test question. Compare and contrast frequency distributions and sampling distributions. Your turn. See you next time.
Simpson, Homer Simpson, he's the greatest guy in history. From the town of Springfield, he's about to hit a chestnut tree.